Yeah, so we're just talking about the method of initial rates, and sort of what this is a differential rate law, and the difference between that and the integrated rate law. So just since I just started recording, the differential rate law relates the rate to specific concentrations. And I was just saying that it's much more useful to be able to relate concentration to time, because you can say things like, when is the reaction going to be finished, which is typically something that you're very interested in. So finally, if we're looking at zero order reactions, this is when it's not dependent on the concentration of the reactant at all, which is a weird case, because it's kind of not what you'd expect. Oops, I got these backed up. Oh goodness. Okay, let me just start over. So the types of integrated rate laws that we look at, you can write an integrated rate law for anything, but for GChem, we just look at second order, first order, and zeroth order. And so in a zero order reaction, we have this equation that describes it, which I just kind of gapped and wrote the equation for something different. And in first order, we have this natural log. A is equal to negative KT plus the natural log of A sub O. And then finally, for second order, we have this relationship here that's 1 over A is equal to KT plus 1 over A sub O. So where do these things come from? Like where do these equations flow from? You would really take like so this would be the integrated rate law. You would take what is generally, we just call it the rate law, but it's really the differential rate law, and you would integrate them. So for a first order reaction, for a zeroth order reaction, that's zero order. That's zero order in the reactant, right? It would be A to the 0, which is just 1. So that's what our rate law would look like. So once you integrate that, you get this expression over here. So if you're calculus sharp, you could do that. And then the same is true for these other ones, right? We're looking at rate is equal to K times A. So here we're raised to the first power, and rate is equal to K times A squared. So there it's raised to the second power. So you can see how you could generalize this. Here we're just looking at first and second order and zeroth order. But if you have the math skills, you can take any rate law and integrate it and have an integrated rate law. Let's see. So one thing that we talk about, which is really just a different form of the rate law, are the half-lives. So that would be kind of the other column that you would have here in terms of looking at kinetics. I need this up a little bit. So we've got the rate law, we've got the integrated rate law. Let's call this the order of the reaction. So it's 0, first, and second. The only other thing that we're concerned about is the half-life. And so you've probably heard the term half-life before. It's not just simply applied to chemistry, but the half-life is the time it takes for half of the initial concentration to disappear. So for example, like if I'm looking at some particular zero order reaction, let's actually write this. So let's say we're going from A to some product. The half-life is, if I start out with say 10 moles of A, the the half-life is the amount of time it takes me to go to 5 moles of A. That's what the half-life is. And so the way that the sort of in terms of calculating what the half-life is and relating it to time and concentration is dependent on whether it's 0 order, first order, or second order. So if we look at the half-life for a 0 order reaction, what we see is that it's not dependent on the concentration at all. We look at first order, we're not dependent on concentration at all. 0th order, we are only dependent on the initial. And then finally, for second order, we just have this expression. So these are just like rearranged. If you go and look up the derivations of these, they're just rearranged versions of, you're playing around with the integrated rate law. So you're saying, okay, how long does it take for half of my initial concentration to go away? And you can solve and get these expressions over here. And so the equation that you're using for a particular problem is strictly just dependent on, what the problem's asking for. Let's see, work through. Let's look at how these things kind of play out in a particular problem. If we did butadiene, let's just continue on. But this is a continuation of the data we looked at in the last thing. We don't need that data. So let's say for a second order reaction, actually, let's say, a good way to put it is like, so a way you might see this presented would be, let's say you're looking at this reaction again, but instead of giving you data to plot, the question might be formulated such that it says, it just tells you a plot of one divided by the concentration of C4H6 as a function of time. Gives a straight line. And so this tells us, the order of the reaction. We'll talk about that. So we can ask questions then. Let's say, our initial concentration of C4H6 is 0.01 mole per liter. What is the concentration at, I don't know, about 15, 1800 seconds. So we've let the reaction progress for, not super long, but some time. And we want to know what the concentration is at 1800 seconds. And so the sort of way we're going to read this is we're saying, okay, well, we've got this plot. The first part here tells us the order of the reaction. So generally speaking, for any type of rate problem that you're dealing with, your first step is going to be able to figure out. So you're going to need to be able to figure out what the order of the reaction is, and then you got to think about what they're asking you here. So here I'm breaking it up and saying, okay, well, this is method of initial rates, and here we have the integrated rate law. But how do you know when to use this equation versus one of these equations? So anytime they're asking for a relationship between, let's say, concentration and time, which is what we're given down here, it's saying what's the concentration at a particular time t, that's going to be an integrated rate law type situation. And then we need to figure out, well, what's the order of the reaction? And so that's what this first part here is telling us. It's saying we took the reciprocal of the concentration of C4H6, we plotted as a function of time, and it gave us a straight line. And so you come up here and you look at we only have 3 rate laws to look at. You say, okay, well, which one would that be true for? And that would be true for this. So all of the integrated rate law equations are in this form of y equals mx plus e. And so if 1 over this plotted as a function of time gives us a straight line, then we know that that integrated rate law fits this data really well. And so it tells us that it's second order. So our reaction is second order. And so we want to know what the concentration is at 1800 seconds. So how do we use this equation? So this problem is nice because we don't have to really solve for much. So let me write the equation out first. So this part, this refers to the concentration at some time t. So you could even put a little t at the bottom to remind yourself of that. So at a particular time, that's what the concentration is. And this is just the initial concentration. And so typically you know the initial concentration because you're the one who's setting up the reaction. So you're weighing out your reagents and such and adding them in. So this is usually a known quantity. And we're trying to figure out, after a certain amount of time, like where are we going to be at in the reaction, or how much of this is going to be left over. So if I started with 0.01 mole, at 1800 seconds, am I going to have a lot of this left over or a little bit left over? And so we have T as well. So what you also need is K. And so in this problem, we're not given any data. So there's no way to really solve for K. You'd either have to be given that or be given some sort of table. So if you're given the plot, if we were given the plot of this, which is what we looked at in last class, you can derive K directly from that. Here we can just say what K is. So you'll notice the units on K can be really pretty wonky. Particularly when you're dealing with the method of initial rates, they get kind of weird. This one's not so bad. But they change the units on K change depending on what the order is for the reaction. Okay, so we've got K, so now we know what this is. And then the initial concentration is just this value. So we're going to plug that in there. And then we also know the time. We're looking at 1800 seconds. So that's what this value is here. And then our unknown is just whatever A sub t is. So we can just solve this. You could rearrange it, I guess, to get A sub t in the numerator, but let's see. More trouble than it's worth. So yeah, so then it's just a matter of just plugging in values. So this is what I mean when I say that this chapter kind of lends itself a little bit better to, at least in terms of problem solving, figuring out what the proper strategy is as compared to acid-base. Once you sort of identify the order of the reaction, there's only a handful of equations that you could possibly use. Why are we using second order again? Good question. Yeah, probably the hardest thing about these is just figuring out what order the reaction is. Let me punch this in my calculator really quick, and then I'll explain that again. So we end up with 1 over A sub t is equal to if we did this right, we should end up with liters per mole, and then we just take the reciprocal of that. And so we see that A sub t is going to be equal to 0.004, I don't know, 7 extra moles per liter. 47, yeah, 475, 47. I'm bad about significant digits. 5. Yeah, so why are we using second order? How do we know that? It's because this first part here, let me clean this up a little bit. It's because this first part here, it tells us a plot of this versus time gives us a straight line. So whenever you're dealing with, when you're dealing with things where you're relating concentrations in time, typically what you're doing is you're looking at the different integrated rate laws and just seeing which one fits the data. So if you were to take, if you're told that the plot of 1 over the concentration of C4H6 as a function of time gives a straight line, that means that it follows this form. That means that if you took and you say plotted the concentration of C4H6, but you took it and did the natural log of it and plotted that as a function of time, you would not get a straight line, so it wouldn't fit that. So you're trying to, you know, what you're typically doing, or a lot of times what you end up doing when you're doing this type of chemical physics stuff, is you're taking data and then you're trying to model that data with an equation. And that's what we're doing here. You're saying, okay, we've got some data that we collected. In this case, we're not looking at it directly. We did in last lecture. And then we were like, you know, we're plotting that as a function of time. We're trying to figure out a model that allows us to kind of generalize about that data. And that's what this is, this second order reaction rate. Is it ever viable to look at the units, the rate constant, and determine the order? Huh. I don't know off the top of my head. Probably. Let's see. Yeah, I mean, I guess, is that true? Yeah, I guess you have to know, if you know the rate constant and you know its units, then you can probably derive the order of the reaction from it. But if you've gotten to the point, I mean, at least experimentally, if you have the rate constant, then you have to know the order of the reaction to calculate the rate constant. So it's sort of inverted. Yeah, sure. Yeah, it makes sense that they would say that you can. It's sort of a backwards way to think about things, in my mind at least, like experimentally. Just because in order to have K, right, if you look at how we calculate K, let's see, is that true? Yeah. If you look at how we calculate K in either case for the integrated rate law or for method of initial rates, you have to know the order of the reaction to begin with. So, you know, from like a experiment, like I guess in terms of like an introductory chemistry class, if you want to give that as a question, you can. But it's sort of backwards in terms of how you would go about figuring it out. Yeah, solubility would be on the exam. Just some KSP stuff. That stuff's not that bad if you got through acid and base. bulk of the exam will be from kinetics, but yeah, we'll have some solubility stuff on there. It'll be solubility. It'll be a little bit light on solubility though, just the stuff we went over. Yeah, so one thing you'll notice is that we're not typically for like integrated. Yeah, I know the exam's coming up really soon. I should probably start out by saying that this last exam kind of period is a little bit compressed. But yeah, our exam is going to be next week on Wednesday. It feels like we just had an exam. So one thing to note about the integrated rate laws is that if you look over here at the differential rate law, I'm just going to write differential above this because I keep calling it that. But if you look at the differential rate laws for these, right, we're only talking about them in one reactant. So we're not seeing things that are of this form where we have like A and B. We're just looking at one thing. We're looking at the rate. We're looking at the differential rate law where the rate of reaction is only dependent on one of the reactants. We don't look at like A and B. And it's not because that doesn't happen. It's just because that gets a lot more complicated. And we're not super worried about that just yet. So typically when you're looking at integrated rate laws, you're going to be looking at things like this, where it's one thing and it goes to the second, or if it has two reactants on the left side, it'll be 0th order in one of those reactants. I'm trying to think of other questions that we can talk about with respect to rate laws. I think this generally kind of gets at the idea. Let me pull up the list of question bank here. I don't move too fast. So typically for integrated rate laws, you're looking at time as a function of concentration. So the data that you'll be given, before we move on. Oh yeah, this is just, I just gave it to you in the problem. If you go back to the last lecture, the place where we get K from is we actually look at this plot for the second order reaction. And you derive K by looking at the slope of that. But yeah, you can't derive K without having any kind of, you can't derive K without having any kind of data. But in the most bare bones way that you kind of are presented with these problems, for method of initial rates, you'll generally be given let's say you're looking at that versus like an integrated rate law problem. The main difference, or the main way to tell which type of problem you're looking at, is for method of initial rates, typically you're given concentrations like A and B, and then in another column, you're given the rates. And we'll have like experiment 1, 2, 3, etc. And so you'll have all these values in here, and you just note that, okay, I'm looking at this and I'm trying to relate it to the rate. And so we're dealing with the rate law in this form. Okay. Method of initial rates deals with the differential rate law. Integrated rate laws, you're given experiments, sort of. But usually what you're doing is, instead of kind of having it set up where it's these sort of, what would you call it? Like, it's not separate experiments here, 1, 2, 3. You're just sort of taking points in time. So you'll see something that looks like this, time, and then you'll have like concentration of one thing over here. And then you'll have like, 0 seconds, 10, 20, 30, 40, and then we'd be looking at like how something over here changes its concentration. So, you know, concentration 1, concentration 2, concentration 3, concentration 4, concentration 5. And so these are sort of the two different things we're looking at. And so these can take on, the integrated rate law relates time and concentration. Those are the two things you're looking at for the integrated rate law. So even if you're not presented data, but you're asked to somehow relate concentration and time, you know you're going to be using some integrated form of the rate law. And that's when you look at those ones that we just looked over, where it was like, this is the first order, second order, 0th order. You kind of determine the order. And here, you relate, this one relates, this one's kind of weirder. It relates concentration to rate. And so your problem solving strategy is just very different between these two things. So if you're not given, so for this one, like in both, in any case, in either case, your first step is trying to figure out what is the order of the reaction and what K is. So in this one, you'd say like step 1 would be maybe to make a plot or look at the plot, more likely is analyze the plot. Analyze plots of concentration versus time to figure out the order. And then step 2 is find the rate constant. We'll just call it K, find K. You can just find K. You find K by taking like any particular data inside of the plot. So you find K by solving the integrated rate law. Using the given data. And then, you know, if there are other parts of this, like, you know, if you know K, if we know K and the order of the reaction, then we can solve for time or concentration using the integrated rate law. And that's most of the scenarios you end up seeing for the integrated rate law. So, you know, the exact way that this ends up presented, it changes, right? Like, so in the last one, it's like, well, you don't actually get data, but it tells you something about the plot so you can figure out what the order is. Sometimes it'll just straight up tell you what the order of the reaction is. It'll say, hey, this is a second order reaction. And so you want to cue in on the fact that we've got time and concentration. And so you know you're going to be doing something with second order. But that's sort of these are sort of the main steps that you go through. So first thing is to figure out the order of the reaction if they don't give it to you. Second thing is to figure out K if they don't give it to you. And then finally, like, you know, if you get the third part of the question can be something like, tell me the concentration at a particular time, or tell me at what point in time the concentration will be this. When we come over and we look at the method of initial rates, it's a very similar type situation, but here typically you're looking at concentration as it relates to the rate, but our first step is still figuring out the order of the reaction. But here we figure out the order by, it's hard to put this one into concise words, but like by, let's say observing effect of concentrations of the individual reagents or reactants on the rate. And so this is where you sort of look at, you know, I'm going between experiment 1 and experiment 2, what's the effect on the rate? And then let's see, what's the other thing? And then, yeah, 2 is you can calculate K from the experimental data. Calculate K from the experimental data and the differential rate law, which again, we frequently just refer to as the rate law, but I like to call it the differential rate law so that it's clear what we're talking about. And then third is we can use, if we know the order, sort of the same thing. If, with K and order of the reaction. We can solve for the rate or concentration. Let's just say rate at a particular concentration. So in terms of quantitative problems, this is pretty much it. In terms of, you have these two different methods that we can use here. We have the method of initial rates and the integrated rate law. In both cases, we're trying to figure out the order of the reaction. We're just doing it different ways. Yeah, I can explain more on that. And then in both situations, you're trying to calculate K. So sort of like step 1, sort of like a really general way to go about this is, step 1 is figure out the order of the reaction. Step 2 is figure out K. And then step 3 is, you know, what are they asking for? Do I use the differential rate law or the integrated rate law? Yeah, in terms of figuring out K, so for example, let's say you're looking at an integrated rate law problem. Let me pull some different data here. So let's say, find something really simple here. Let's say you've got ethanol. So this is a nice one. I think we even talked about this a little bit in class. Let's say you have ethanol and it's being metabolized in your liver to acetaldehyde. So one thing you'll notice about these problems is that we don't, like in the equilibrium chapter, we're really focused on the reaction itself and its stoichiometry and how that all ties together. And it's not to say that that doesn't matter for these, but you'll notice in the problem solving like workflow, that's less of an important thing. We don't really look at the coefficients on the reactants or anything. But so you'd be given data like this, time, I'm gonna get myself into a situation because I don't actually know if this is first order. I guess I could look it up. And let's say that you're given, so we're dealing with gases here, which is fine, it's the same idea. So initially you start out with a pressure of 250 torr. Oh, I see. Yeah, this isn't what happens in the body. This is you're doing this over like copper or something. Why would you have ethanol as a gas in your body? Unless you're having a wild night if that's going on. But you're given all these concentration values for ethanol. So note here in this problem, one, remember for integrated rate laws, we're only ever looking at one thing. We won't have more than one column of data here, or if we do, you'll note that one column is 0 order. So we're just looking at this one thing here. And we're looking at how its concentration is changing with respect to time. So questions that you could ask about this is like, you know, they all end up kind of being the same. So we would want to know, like, what is the order of the reaction? So yeah, so how do we find the order of the reaction here? So you want to take plots of concentration versus time. So if we thought maybe it was 0 order, let's say you've got this. So these are the different types of orders that it could be. It could be first order, 0. I always forget 0th. It could be 0th. It could be first. It could be second. How do we know which one it is? Well, what you want to do is you just want to take and plot the concentration in these different forms here. Trying to see, let me see if I can just look at the answer real quick because I don't want to have to do the plot. Yeah, so generally speaking on an exam, we're not going to ask you to plot these. I feel like I've had to do that before, but it sucks. There's a couple of, there's some ways you can figure it out by trying to get the slope of the line, like seeing if it's the same at 2 points in the curve. But that's not really our kind of goal here. So let me quickly look up what the damn chapter 10. Here we go. Chapter 35, rate laws. What's that first order? Rate law equals negative KT times this answer is terrible. Is it second order? I think it's second order. Let's see. Okay, it doesn't really matter. Let's just say. So we go through and we do the plots. And let's say that we find that the plot of 1 over A versus T gives us a line. And so we know it's second order. So this tells us okay, so now we want to know what K is. So yeah, okay, it's true. K is whatever M is here. Well, it's negative K. Because we're looking, well, actually, sorry. Get this backwards because it's the second order. K is not negative, it is positive. So it's true that, if you look at graphically, the slope of the line is what K is, but that doesn't really matter that much. I mean, unless you're given a very specific question where you're given a plot, the easiest way to figure out what K is to just use this equation here and then use the data that we have. So if we know that the data that describes this is like this, all we have to do is we can pick any row here and solve this. So once you know the order of the reaction, it's like, well, what is A sub 0? That's whatever my concentration is at time 0. So I pick that as the point for A sub O. And then, what is A sub T? Well, it's whatever we want it to be. If we pick time equal to 100 seconds, then a sub t is 237. If we take time equal to 200 seconds, then a sub t is 224. So I guess one way you could do this if you didn't want to deal with graphs, I think this is how I kind of got away with it when I used to have to do these in college, is you can check. So this is true at t, actually I can put, so at 200 seconds, we know that's true. But so now we know all the different kind of pieces that we need to solve for k. So I chose initial concentration is just whatever your concentration is at t equals 0. Oh, yeah, sorry. Yeah, for the other ones, it's the opposite because the slope is negative. But so, yeah, so if you've got this, once you sort of have whatever your initial concentration is, which we got here, which is at time 0, then we just pick a point, and it doesn't matter which one. I just arbitrarily chose this one. And then I can solve for k from that. So I've got, for this particular time, I know the concentration, and then I know what the initial concentration is. And so all I have to do is solve for my unknown, which is k. So one thing we could do here, because I don't want to deal with the plot because there's no way in hell I'll be able to plot it accurately on this sheet, at least not in like any kind of time period that's useful. One thing you could do though is solve for k, let's say at 200 seconds. You'll get some value. I'm not going to walk you through the algebra, but I'm sure you're capable of doing that. But then you can solve for k, let's say at 500 seconds. And so even if you didn't do a plot here, this is sort of a check for linearity in a sense, because if k, so if this thing is described by a line and the slope is k for the line, then at 200 seconds, my calculation for k should be the same as it is at 500 seconds. So it's sort of a way to check to see if you're actually correct and whether it's first order or second order. So if your k is different, let's say, in going from 200 seconds to 500 seconds, that means you, assuming you didn't screw up your calculation, that means that you're not actually second order. So I assume this was second order because the answer in this whatever problem book I looked up was not super helpful. But if it, we would be able to quickly find out if that's not true. So one thing you could do is like I'm out of time here, otherwise I would do it with you guys. But you can look at different times and calculate the k value for it. And if you're using the correct equation to describe the data, then your k value should always be the same or very close with an experimental error the same. And if I'm using the wrong one, then I know it's the wrong one. Like if I'm using the wrong equation, then I get a different k for each experiment. And that tells me that it's not actually a line that I'm describing. And so I need to try a different model. But yeah, so generally though, calculating k comes from figuring out the order of the reaction. And then once you know it, you just take some of your experimental data and you plug it back into the equation. And the same thing is true for the differential rate law, right? So let's see, what's today? Monday. We've got an exam next week. What other crap do we need to cover for kinetics? I think the only other thing I really want to get through, maybe we'll spend a little bit more time on integrated rate laws. And then we'll look at reaction mechanisms, which can be a little bit confusing, but are, I don't know, kind of the point of the whole chapter in some ways, and catalysts and stuff. But catalysts are pretty easy to figure out. But yeah, we'll look at what a mechanism is versus what we're used to seeing, which is the overall reaction. So like this is the overall reaction, but it doesn't actually describe the mechanism. It doesn't describe the path that we take to get between the reactants and the products. And that's sort of a a key thing. Yeah, we'll look at radioactivity. Yeah, we should have time to look at radioactivity. Radioactivity is actually straightforward because it's always first order. So you're always using, if you know it's a radioactive thing, you're like, okay, it's first order, and you just reach for your first order equations. The hard part, in my opinion, teaching this, the hard part is figuring out which equation to use. Figuring out the order of the reaction is really the main challenge. And once you have that, you immediately know, whatever equation you're supposed to use. There's conceptual questions we can ask that are pretty like ruinous, but we're not intentionally trying to do that. But yeah, we'll look at radioactivity. But so if you can get, I think the main thing to focus on though at this point is like, I feel like method of initial rates, like they're all the same problem, like kind of over and over again. Once you kind of get a handle on it, it's not that bad. Integrated rate law, it's kind of the same thing, but there's just a little bit more to deal with. So play around with these integrated rate laws, and that's most everything that you need to know. When we look at half-lives and stuff, especially for radioactivity, you'll see that if you get this, that stuff is like a really easy step forward. And then reaction mechanisms feel like they're really different. And they are a lot different, at least in terms of problem solving strategy. But if we spend a little bit of time on that, I think that'll come together quite nicely for you guys. So, all right. Yeah, so method of initial rates, integrated rate law. We'll look at, maybe on Wednesday, we'll kick off looking at some half-lives and some radioactivity stuff, since I haven't really worked in that in class yet. And then we'll move into reaction mechanisms and looking at catalysts and stuff.
So Wednesday, we're talking about half-life?
Yeah, Wednesday we'll talk about half-lives. Let's just plan on doing that. And I think I think the half-life stuff, I always think it's going to take less time than it does. But I think the half-life stuff will go pretty quick. If you get this stuff, the half-life stuff's not that bad. The practice problem sets, if you go in the GChem website, they have some really good practice problems on the GChem website. So click on that link and you'll see a whole bunch of stuff. That's what we're kind of looking at for the exam. Yeah, we can go over whatever questions 4 and 5 in the office hours. Let me take a very quick break and drink some water, and I'll be right back.
I wanted to know if you could move down a little bit. Oh.
All right. So I'll just start with this question from
In the modules, it seems like it's supposed to be like a second order reaction, but I don't see how we're supposed to know that. Also, when we're doing the modules, it's not, whenever we finish one in an attempt, it's not giving us the answers or an explanation.
Bummer. Should give you the answers at the very least. That's probably a setting. Let me see, actually, I can probably fix that right now.
On the homework, it gave the explanations, just not the answers.
There's probably just a little widget to click on. Yeah, so I think in the problems that you're looking at for LE 3.06, I think in those you want to figure out the order just using the initial rates kind of method, where you take the ratio of the rates and set that equal to the ratio of the concentrations and solve for that. That'll give you since it's only in one, so it's only in A, that'll give you the order of the reaction. But let me see, let me fix this LE. Let's see quiz responses. It should have given you, it did at least give you the correct answers at the, it should have given to you at the end at least. Anyway, I just changed it to where it'll give it whatever after each one. I guess it doesn't really help now, but it should have given you the correct answers at the end of the homework. Okay. Yeah, well, let's see what we're looking at here. So we got question 4 and 5. We're good, they use the same data, so I don't have to spend a lot of time writing out the set here. So it says, consider a reaction going from A to B. And it says, use the data below to determine the first half-life for experiment 1. Please answer in seconds. It's sort of a weird phrasing, to me at least, I don't know. But all they're asking you for is, they're saying, okay, for experiment 1, we're given this concentration of A, we're given this concentration for I guess for experiment 2, we're given a different concentration. Interestingly, A is increasing. Oh, I see. You're just you're not increasing because you're not doing it with respect to time. Sorry. So we're changing the concentration of A, and we're seeing what the effect is on the rate. That's the right way to think about this. Okay. And so the question is, like, what's the first half-life? And so, yeah, you're correct. You need to figure out that this is second order. How do we figure that out? So when you're given, and this is what I was trying to kind of dig on in class, is if you're given rates and concentrations, that's when you're using the method of initial rates. And so if you're trying to figure out the order of the reaction, you can start out by we can write out a general rate law for this, which is just that rate is equal to K times A raised to some power. We're just going to call it X. And this is just, you can write this out for any reaction. You just take the reactants and you multiply their concentrations to one another and you raise them to some power. We don't know what that power X is. That's what we need to figure out in order to figure out what the half-life is, the appropriate half-life equation. So this one sort of merges the integrative rate law together with the differential rate law in a sense. So here we're going to use the differential rate law to figure out the order of the reaction. And then once we figure that out, we'll use the integrative rate law to figure out its half-life or whatever. So what does this come out to be? So if we look at, let's say we take the initial rate for experiment 2, which is 0.01, and we're going to put that over 0.0025. These are dimensionless because we're taking ratios with the same unit. We can set that equal to the concentrations 0.2 divided by 0.1. So just to be clear where these things are coming from, experiment 1, concentration from experiment 1, initial rate from experiment 1, those go on the bottom. And then concentration 2 is over here, initial rate 2 is up here. So if we want to figure out what X is, we say, okay, like we've got this ratio, how is it related? How does the rate change? So when I take this, what am I doing here? Quadruple the concentration here. Double the concentration. What happens to the rate and how is that related to this power? I kind of just gave away the answer. It's that it quadruples. When I double the concentration, I quadruple this, but we can solve this So 0.001, I'm sorry, 0.01 divided by 0.0025 is equal to 4. And so you end up with this 4 is equal to 2 to the x. And we see that x is equal to 2. And so because now we know that x is equal to 2, we can come back and look at our equation over here, and we just plug that in. And so we know that the rate is equal to k times a squared. And so it's second order in A, but it's also second order overall because A is the only reactant.
So are we allowed to just, why are we allowed to just ignore the k when we do 0.01 over 0.0025 and then the concentration over the other concentration?
Why don't we worry about k? Is that the question?
Like, why are we allowed to even set them equal to each other without k, I guess?
Like some fundamental question.
Oh, is it because the k's would just cancel each other out?
Yeah, I guess that's you answered your own question. Yeah, whatever the effect is, I guess whatever the effect is on since k is constant, whatever the effect is on the initial rate of k, we're not going to be able to see that anyway. Yep. Does that make sense then? So all you're doing is you're looking at the effect of concentration and how it changes on the rate in this. And sometimes this can get a little squirrely over here. I don't know if it, if you have to use logarithms or something, you can get squirrely, but I don't think we really see that. As long as you put the larger number on top, you generally end up with a pretty easy thing to solve. But yeah, that tells you if it's second order. And then you can go through, is it clear kind of the rest of the problem once you get there, Ian, or you want me to go through the rest?
I think it's clear.
Yeah, so you solve for k, and then you take the integrated rate law for second order and just use the half-life equation for that. Same thing for the next problem. But the tricky thing about this one is just that it combines the integrated rate law with the differential rate law. I actually like these questions in that regard, at least.
Can you tell us how to find the second half-life of number 6? Because that's the one we were all getting stuck on.
For problem 6, the same data. Let's see. So we know it's second order. So what else do we know? What does k equal here? So k is equal to any of these. Has somebody solved for k already? I can solve it. So let's just say k is going to be
0.25.
0.25. Okay, good. Let's see. I should be looking at the units out of that. If they should be, since this is squared, this will be molar squared per second. So we want this to be probably inverse molar. I think that fixes that. I think that's the units, and then inverse seconds. Okay. And so now we just want to know what the half-life is. So then we just use, you can either use the original equation or you can just look up the half-life equation for a second order reaction. And we see that T sub 1/2 is going to be equal to 1 divided by K times A sub O. So let's see, so what are they asking for? Second half-life, the second experiment. So we want to know the time. I think what they're asking for is the time at which this is part of the question I don't like. But I think what they're asking for is the time at which the concentration of A is cut in half. So we just want to say t sub 1/2 is equal to 1 divided by k. So I think the tricky thing is just actually I'm kind of confused with what they're asking for. Oh, the second half-life. Ah, okay. This is such a weird thing. Okay. So yeah, they're talking about, I was confused with what a sub 0 is. So yeah, so okay. So in experiment 2, we start out, I guess we're calling the first half-life, a sub 0 is equal to 0.2 molar. So if we want to call that, I guess like half-life 1, maybe this is how people talk about half-lives, I don't know. But half-life 2, that's when, I don't know which one to call this, a sub 0 prime. So the first half-life is sort of the amount of time that it takes to go from 0.2 to 0.1. And then the second half-life will be the amount of time it goes to from a sub O prime, let's say, to a sub, I don't know which one to call this, I'll just leave it as a. But that's going to go from here to 0.05 molar. So that's our half-life 2. So I think it's just the phrasing of the question is a little bit weird. But so then you just want to plug in your initial concentration. Yeah, okay, good. I did the units right. And it ends up being whatever that works out to be, 0.1 times 0.25. Oh, good. It should be 40, at least according to them. Yeah, 40 seconds. But yeah, the confusing thing is just like the way the question is asked, which it took me reading a couple of times to realize. So in 4 or 5, let's see, in 5, they're asking about the first half-life. So they're saying the first half-life is like what it's going to take from go from 0.2 to 0.1. And then the second half-life, means that you're going from 0.1. So you're starting here, 0.1, and then you're going to half of that. And so the amount of time it takes is this, but yeah, you just need to be careful that you plug in the appropriate value.
Is there an easy equation to derive? Like, so if we had to calculate the fourth half-life, what's an easy equation that, so we don't have to do it step by step? Is there just one equation?
I don't know. I'm not sure. I'm not like the first half-life, second half-life. I don't have one off the top of my head. Usually when you're, let's see, how would you do that? So if I know, I guess you could calculate the general half-life. Let's see. So if the half-life, I guess what you would say is, so if you know, so like let's say in the first problem that we looked at, so you're looking at the first half-life ever. Another way you could do it is just say, so if I know that the half-life is equal to 1 over k times a sub O, then I know that the half-life, the better way to say it is probably just to look at the half-life for the initial concentration there and say, well, okay, it's 1 over 0.25 times 0.2. And we come out with the answer that, what is that, 20 seconds. So that means every 20 seconds it's going to be halving. So if you want to look at the second half-life, you just multiply that number times 2. You want to look at the fourth half-life, it's that number multiplied times 4. Does that make sense? So every increment of 20, it's going to halve. So again, I'm not totally sure if this is the language that people use for these types of things, like second half-life, third half-life. I didn't write these questions, and I'm not super familiar with half-lives, so. But using their language, this is, how would you calculate it? Once you know the half-life, it's just a multiple of whatever that is. The first half-life is 20 seconds. The second one is 2 times 20 seconds. The third one's going to be 3 times 20 seconds.
So is for second order, so every subsequent half-life is just going to be doubled, or it's going to be multiplied by n, I guess. And then for first order, it's just the same. And then for zeroth order, is it just half? Every subsequent half-life is, or divided by n? Would that be a way to look at it?
Yeah, I think regardless of what order you're looking at the half-life, let me think about it.
Or like n times. Oh, okay, it'd be.
I don't want to say
by 2k.
Yeah, I'd have to think about it, but I think generally speaking, the half-life is, if you know the half-life, for example, is like 10 minutes, then what we're saying here always holds true. The first, how long is it going to take for the concentration to go from 100 to 50? It's going to take 10 minutes. And then how long is it going to take to go from 50 to 25? It's going to take 10 minutes. And so I think that's true regardless of the order of the reaction. Like, I think that's just kind of the definition of the half-life. Although, let me think about that. Because then you're dealing with. Honestly, I'm not sure, Ian. I have to think about it more carefully. It's a good question, though.
Why is the equation to work out the second half-life the same as the equation to work out the half-life for experiment 1? Like, it's
I think
still
it's
1 over 0.25.
It's the context that it's asking for. A better way to word it would say, the way I would have worded the question would have been, how long does it take to go from 0.2 molar to half of its original concentration? And then how long to go from the initial one to a fourth of its concentration or something like that. It's just whatever you plug in here, the half, this T1 half that you're calculating, is just saying at what point you'll have half of that amount left over. If that makes any sense. I don't know. It's the same equation, like the half-life. Well, actually, yeah, that's a good question. Let me think about that.
Asked for it. You put in A initial, A sub 0, but it asked for experiment 2, and you use A sub 0 for experiment 1.
Yeah, so it's not truly A sub 0. It's like A sub 0 is changed in a sense. Like you're talking about in experiment 2, you're talking about the initial concentration. So in the first problem, you're talking about the initial concentration being 0.2. In the second problem, we're talking about the second half-life. So the initial concentration is now different because you're talking about it after it's happened. It's like, I know it looks like you're plugging in the same value. You can put a prime on there. That's why I put that prime up here. If it makes you, so that there's not as much confusion in terms of the algebra. Ian, did you have some clarity to put around that?
Yeah, so it's like after you take the half-life of 0.2, half of it is gone, so you're only left with 0.1 molarity, and so you're taking the half-life again, and that's why it's the same as the first one, right? Because half of 0.2 is 0.1, and then now you're just taking the half-life of that, and we already did that in question 4.
Does that help at all, Taylor, or is it so confusing?
Yeah, it helps.
I agree, it's a little bit confusing. It took me a second to understand what the hell they were asking for, so I wouldn't feel too bad about being confused there. But yeah, once it clicked, I was like, oh, okay.
So usually for like second order half-life, there's not going to be like a weird equation, or there's not. It's usually going to follow like each subsequent half-life is like 20 seconds, and 20 times 2, 20 times 3, 20 times 4. Right.
Yeah. Yes. I think that's sort of the power of the half-life, is that it's just a kind of a general descriptor of. It's just sort of a general descriptor of what's going on. What am I trying to say? like if the half-life's, some number, 10, then it makes it really easy to kind of do those back of the envelope type calculations without having to do a whole bunch of modeling, without having to use the actual rate, integrated rate law. I think that's sort of the benefit of using half-lives. Because otherwise, like, what are you really talking about? If you think about it, like if you look at the integrated rate law for a second order reaction, you could ask this question for the integrated rate law. You could just say, well, I'm starting with 0.2. When do I end up with 0.1? And the integrated rate law will find that for you. And so I think the benefit, you can use the equation to find any concentration. I think the benefit of the half-life is it's just like it's just a numerical way to describe it that doesn't require an equation at all. The half-life's 20. If the half-life is like 10 years for something, then I know, after 10 years, I'm going to have half of it. And then after another 10 years, I'm going to have half of that. After another 10 years, I'm going to have half of that. And so I think that's what the benefit of the half-life is.
Okay, cool.
First half-life. Oh, wait, am I saying that right? Hold on, now I'm reading in the textbook. I might be questioning that. Whatever case of A. Did that work out so cleanly? Now I'm confused. Is this true? I guess is what I'm wondering. So if we look at, I think maybe the answer is no. I take that back about doing the multiples. So I'm thinking of like so for second order, does it just work out cleanly here? Let's see. So let's say we do want to find T1 half and we want to figure out where, let's say our initial concentration is something really different. Let's say that it's like point. So we're going from 0.2 to 0.1. Let's see, to go from 0.1 to 0.05, what happens if we go to 0.05 down even further? Yeah, that would be, so it would take 80 seconds to go from 0.05 to 0.025. That hold then, so let's see, 0.1, 0.2 to 0.1, that takes 20 seconds. 0.1 to 0.05 takes 40 seconds. But then they go from 0.05 to 0.025, now it takes 80 seconds. Okay, yeah, so it's what I said is wrong about it being a multiple. I think that might be true for first order reactions, but not for this one. So I take that back. So I don't know how to do, let's see, how would you do that? If you wanted to find like the 80th half-life or something. I don't know, we could probably work that out, but the main thing is just I take back what I said earlier about just being able to take a multiple of it. I think that just coincidentally worked out for the first one. But we can see that, let's take a look here. So if we have, let's get rid of the A sub 0. Let's say we're at A, and we're kind of watching this thing change with time. I haven't had a chance to think about the math behind this yet. So yeah, so 0.2, let's say we're starting the clock there. We know that it takes 20 seconds to get there, and we just calculated it takes 40 seconds to get there. but then it takes 80 seconds to go from 0.05 to 0.025. And then if we want to calculate it again to see what how long it takes to halve 0.025. Yeah, now it takes 160 seconds. Yeah, okay. Yeah, so that's wrong. So you'll notice it's not a multiple at all. It happens to be a multiple from going from here to here, 0 to 20, 20 to 40. But then you can see that it's doubling each time, sort of geometrically, 40 to 80, and then 80 to 160. I think if you wanted to kind of figure out where you were going to be in the reaction for like a particular half-life, I'd have to think about how to derive sort of a general equation out of that. But I'm not entirely sure. But the reason that it changes like this, so for this one, I'm sorry, for the equation for it, we see that T1 half is equal to 1 over K times A sub O. And so the half-life is dependent on the concentration of whatever you have for the second order reaction. So like as my concentration changes, we see that the half-life will change as well. And so we don't expect it to be a multiple when we look a little closer at it. I think we do maybe expect it to be a multiple when we're looking at it for first order. Because in a first order reaction, there T1 half is equal to 0.693, which is a constant divided by K. So it doesn't matter what the concentration is that we're starting at. If I'm at, let's say 0.2 again, and we use this equation, what we should see is that it just changes linearly as we move forward. Let's see, so yeah, so to go from 0.2 to 0.1, I don't know, let's say our half-life is 10 seconds. That would be, it's just going to be a constant rate. I guess that's all that really matters. That's all we're really saying, right? So if this equals 10 seconds, whatever K is kind of dictates that, then that jump between that to that is going to be kind of constant. So that's where things would be kind of like we were talking about before, where it is really just a multiple. But just to be clear that I was wrong when I said that earlier, here it does not change linearly, and that's because you have a concentration term in the half-life equation.
I think I tried deriving an equation, and maybe we can test this. Like, if we have like T of 1/2, and we'll say to the power of n, this just represents like the half-life of n. It says equal to 1/2 to the power of n over k times the concentration of A at the point. And so because the concentration of the A is something we can easily find, so we just say like, we just take the half multiple times.
Yeah, what you're describing is kind of what I was imagining too, is maybe looking at multiples of the, or half n times. I'd have to think about it, but yeah, something like that. But yeah, in general, I'm not sure how the half-life problems crop up. I'll have to look through those. I just think of them as being like extensions of the integrated rate law, but clearly I should need to think about them a little bit more. So, well, we'll talk about it in class on Wednesday. Let me see what other, now that I've sufficiently confused you guys about half-lives, let me see. K from the previous problem. Maria, I'm not sure what K is on the previous problem. Up here, whatever this is. Yeah, I'd have to go through and calculate it. And I'm not even 100% sure that this is second order. What am I doing on time here? But yeah, we could figure this out really quick. We could say, let's say, so if we have 1 over A sub t, let's say we're using 224, is equal to K. 200 plus 1 over a sub o, which we said is 250. Oh, I should have solved for k. Sorry. Let me be more precise about this. I'm being sloppy, leaving my units off and stuff. Okay, so let's solve this equation for k. So we've got 1 over a sub t minus 1 over a sub o divided by t equals k. So this is a solid check for figuring out if something, what the order of something is. You could just solve each one for the slope and check to see if the slope is the same at multiple points. We'll figure that out real quick. So what do we have here? We've got 1 over 224 torr minus 1 over 250 torr. And that's all divided by 200 seconds. So that'll give us one value of k. And then we can look at, a different value of k. So we could say, what if we looked at, I don't know, let's say 500. So what about here? So we could say 1 over 185 torr minus 1 over 250 torr divided by whatever the number of seconds is equal to k, and sort of compare those and see if that is correct. Reasonably small rate constant here, so for this one I come out with k is equal to 2.8 times 10 to the minus 6. What's that? Torr. What are units on that? It should be inverse torr seconds or something. I think that's right. And then let's see for the other one. Yeah, I get the same thing. 2.81 times 10 to the minus 6. I'll double check that first. I might have just punched the same thing in my calculator twice. Oh yeah. Yeah, now I'm not sure if this is second order or not. I think it is. I think it's within experimental error, but I'm not 100% sure. But yeah, the rate constant should be somewhere around like 2 or 3 times 10 to the minus 6, I guess. Actually, I have the answer in the back of the book. I expect it to be the same. Right, like I know it should be the same. I just don't know how precisely the same they should be for both of them. There we go. Get a rate. Oh, that's a different problem. Oh no, yeah, see they're saying rate is different. It's 1.7. Negative KT. Negative KT plus. Which rate law is that? Is it 0 order? It might be zero. That might be a zero order reaction. Anyway, so yeah, so I made a guess that this was second order in ethanol. And I think what this is showing us is it's not, because we get two different K values here, trying to make things get confusing. But generally speaking, when you want to calculate these things out, you just plug them back into the equation that you're using. This is the part that's confusing here. Is just that I'm using the wrong equation, but that's just because I didn't do the plot properly. But this is a check to see if you're using the right equation or not. Let's snag this, because now I kind of want to know. Okay.
Can you also make
Yeah,
sure that next week's modules and homework have the explanations and the answers given after an attempt?
Let me see. Which week are we in? November 2nd? Yeah. Yeah, it looks like they're there. Let's see. Let students see the correct answers. Yeah, I think it just got checked wrong for one of those boxes, so should be good. Okay. So yeah, if we're using, I wish this thing had a way to plot things really easily. But let's say, so it's not second order, so we know it's not second order. So one way to go about this, it's not the easiest way, but it's, I don't know, probably still preferable to graphing, is to just go through and check the different equations. So if I assume that it's second order, then I'm saying, well, this data should fit this and it should be linear. You know, it says that this basically tells me that after some time t, if I multiply that times k and add it to 1 over the initial concentration, it'll give me the inverse of the actual concentration. And so k should be constant for any one of these individual experiments. So when you're calculating k, because I think that's really the root of your question, what you want to do is you just want to take your initial concentration as just whatever this is. So t equals 0 is initial concentration. So that ends up being your concentration for A sub 0. And then you want to plug in some other value for your other concentration over here. So you pick some other time, and you plug that in for this, and you plug in the concentration value for A. But since we just tried this, we know that that's not going to actually be second order. So we can try another one. So let's see, since this is being done catalytically, let's see if it's first order, zeroth order. So now we can try and calculate k from this. Let's see, k would be equal to here. And so now we can go ahead and say, like, okay, well, what about, we can test it at two different times. We can say k at, let's say, I'll just do the same one. So we'll take 224 minus our initial, which is 250, divided by the time associated with 224, which is 200. So that data corresponds with this. And we could see what that comes out to be. I'm going to be sloppy with my units. Oh, this is negative k. No, I'm just generally confused. Maybe I'm looking at the wrong problem in the back of the book. Yeah, anyway. Who was asking that? Maria. Yeah, so Maria, I'm sorry, I'm doing a terrible job of explaining this. Mostly just because I can't figure out what the damn order is. This is the problem with coming up with doing problems ad hoc during class. But generally what you want to do is you just want to solve for K for the particular reaction, and that's sort of your general workflow for it. If you want to check, like for example, for office hours on Wednesday, if you want to make a plot of this data and figure out what the order is for it, and solve for K for that particular order, that reaction, we can work through it then. But it'll take me, I'll have to go through in like Excel or something and plot it, and that's going to take me a little while. Although at this point I've reworked it so many times, I'm not sure. It would have been faster just to do that. Hopefully that didn't like super confuse you. Let me open up this up. So yeah, so all I'm doing is I'm punching this data into a spreadsheet. And now I'm going to take a look at some graphs for it. Actually, I think I can share that screen with you guys. Let me do that in a second. The time. Here we're looking at pressure. It's like a natural log of pressure. And we can look at 1 over pressure. Hold on, let me share this screen. Okay. Yeah, so I made this little Excel spreadsheet here. And then let's take a look and see what we get here. So if we insert a plot for this, looks pretty linear to me. It's hard to say with the damn scale. Versus that looks very linear. I think maybe the first one won't look linear once we kind of zoom in on it. I lost it. There we go. Okay. Well, maybe the data. Oh, that's correct. And then we'll select some data for this. Y function of. Let's see, so we want our x to be this. I think that's the problem with some of those other ones, although it shouldn't matter that much. And then we want our y to be this. You can see why I was resistant to do this, even with the plotting in Excel. It's still a pain in the ass. But yeah, let's go ahead and okay. All right, I think that's all right. I hate this new version of Excel. Format. Nope. Really just want to get this axis smaller. Ah, there we go. Minimum. 0. It's hard still to see. I'm not sure what the expectation is in terms of being able to like do this by hand in like a plot. So what happens if we add a trend line? It's like so subtle. All right, I'm sorry. I feel like I'm going way off the rails here, but if we look at this graph here, for example, so this is a graph of concentration, time. Yeah, concentration 1 over the concentration as a function of time, and you can see I tried to fit a line to it, and it's a little more subtle than I'd like, like for instructional purposes, but you can see that the line doesn't really go through the points very well. And the same would be true if we looked at, this one's small. The same would be true if we look at this one, where we're looking at time versus pressure. If I try and fit a line to it, let's say I add a trend line to this. Man, that fits pretty goddamn well. R is equal to 1 to m. Yeah. What about log then? Yeah, I guess that's that. This is like such a subtle difference between these. So the best fit, I guess, for a line is going to be 0th order. And then, so I guess K would be, if we put the equation on here, we should be able to get K from it. I'm out of time here. All right, how about this? I'll pick up, this is kind of going off the rails here. I'll pick up on Wednesday with an example of how to just kind of work through just to find the value of K, because it's really all we're trying to do here. This is just getting, so let's look at our equation on the chart. Yeah, I don't know. Yeah, all right. I'm gonna back out of this Excel nightmare I'm in. Go back to my iPad. Okay. So anyway, so I don't know what the hell's going on with the data. I'll take a look at it and start out class on Wednesday with it. But generally, just solving for k is actually straightforward. I'm just making it super confusing because I'm trying to get to the bottom of like what the hell's going on here with the ethanol. Let's see. Yeah. Any other questions before we go? Maria's not even in here anymore, so hopefully. So anyway, the workflow there is that what you would do, you would just plot straight lines. I'm probably just working fast and like mess something up. But you plot straight lines and then you can derive all the data that you need from it or figure out which integrated rate law to use and calculate k from that. It's reasonably straightforward, although it doesn't look that way from the way I'm working on it. And k should be the same. The only point I was really trying to make in the first thing is that the k should be the same regardless of which experiment you choose. Just things get a little bit weird. I don't know if it's the data or if I'm just punching through the numbers too fast, but anyway. All right. On Wednesday, we'll pick up. I'll kick off working through one of these k things. We'll look at half-lives pretty quickly. And radioactivity, which is kind of related to that. And then we'll kick out into reaction mechanisms, which can sometimes be a little bit confusing, but are, in my opinion, the more interesting part of this chapter instead of this kind of quant stuff. All right, I will see you guys on Wednesday. Thank you for being patient while I got super confused in Microsoft Excel there.